Okay, let's talk about something that happens deep inside the machines that build our world. You know, when you're trying to make something super precise out of metal.
Right, like a critical engine part, maybe, or something for aerospace?
Exactly. And the cutting tool, it's like the star of the show. But this tiny little tool faces these, well, relentless enemies right where it cuts.
You mean the heat and the chips?
Yeah, intense heat enough to actually distort the tool itself, and then these razor-sharp metal chips flying off like crazy.
Uh-huh. They can cause real havoc if they're not managed properly.
They're not just minor annoyances, are they? The source material suggests they're like fundamental forces fight against accuracy, efficiency.
Absolutely. Mastering that battle, that unseen fight, is critical for making perfect parts consistently. It's the difference between smooth sailing and constant problems.
Problems like what? Damaged parts, tools failing early.
Exactly that. And unpredictable processes, which is a killer in manufacturing. So managing those two things, the thermal stress and, the physical challenge of controlling the chips, it's just paramount.
Which brings us to the material you shared. It really digs into how Iscar is tackling these specific issues.
That's right, their approach.
So our mission for this deep dive is really to unpack those innovations highlighted in the source. We're talking about their direct cooling and the advanced chip breaker geometry.
Yeah, understand how those specific things change how tools perform, how parts get made.
We want to see, based on the material, how this fundamentally shifts things.
It moves us past thinking of a tool as just, a hard shape. This source shows it's more like a highly engineered system.
A system where tiny details inside, on the surface, they have huge effects.
Dramatic impacts, yeah. On how smoothly things run, the quality you get, and ultimately how efficient your whole production line is.
Okay, let's get into it then. The material, it starts by really emphasizing thermal management and chip control. Why are these singled out as the core problems?
Well, think about what's happening right at that cutting edge. The friction, the metal deforming, it creates just immense heat.
Okay.
And if you don't manage that heat, it degrades the tool, it wears faster, or worse, it can deform plastically.
Meaning it actually softens and loses its shape.
Kind of, yeah. It loses that precise geometry. And at the same time, that chip peeling off, it's hot, it's sharp. If it doesn't break and get out of the way,
Trouble.
big trouble. It can pile up, scratch the part you're making, put weird forces on the tool, leading to vibrations, maybe even breakage.
So these aren't just like side issues. They directly hit the accuracy and the finish of the part.
Directly. And the approach described in the material, it doesn't treat them separately, does it?
No, that's a key point.
Yeah.
The strategy presented for Iscar, it's combined. It pairs these advanced internal cooling systems with high-performance chip breakers.
Addressing both things together, the heat and the physical chips.
Right, so let's focus on the cooling first, this direct cooling idea. What was the real need driving this kind of innovation?
The material points straight at modern manufacturing, especially mass production. You need super smooth, really stable cutting. You need the longest possible tool life, and you need that surface finish to be consistent part after part after part.
And just flooding the area with coolant doesn't cut it anymore.
Not for the really demanding stuff, no. Standard flood cooling just isn't precise enough. The need was for something much, much more targeted.
Okay, so how does this targeted cooling work? It sounds like more than just squirting coolant nearby.
Oh, it is. It's about really innovative coolant channel design inside the tool or the insert itself.
Inside, so you can't even see it.
Exactly. The material tells us it's about optimizing things like the outlet angles of those channels, the exact positioning of where the coolant comes out, and controlling the flow rate.
Wow, so it's about hitting the absolute critical spot.
Precisely. Directing that high-pressure fluid right to the cutting edge and where the chip is actually forming. Maximum effect, minimum waste.
And the benefits. What does Iscar highlight from getting coolant right there?
Well, there are several big ones. First, a significant drop in heat on the insert.
Which is key because of that plastic deformation risk.
Absolutely crucial. Imagine the very tip of the tool slightly softening under heat and pressure. It changes the geometry just enough.
To mess up your dimensions or the finish.
Exactly. Targeted cooling keeps that edge temperature stable. It prevents that sneaky deformation, preserves the tool's accuracy, preserves its life.
So it basically keeps the tool's integrity under fire. Makes sense. What else?
Another major one is efficient chip evacuation. Uncontrolled chips, they can be a nightmare.
Yeah, tangling up, scratching the part.
Or building up and messing with the cut itself. This focused stream of coolant, it helps blast those chips away continuously.
Like a little power wash, right where the action is.
Pretty much, yeah. That prevents buildup, leads to much more stable cutting, and a cleaner surface finish on the actual workpiece.
Okay, what about this built-up edge?
Ah, yes. The material notes the prevention of built-up edge formation. That's when bits of the workpiece material, especially with some stickier alloys,
Actually weld themselves onto the cutting edge.
yeah, it completely changes how the tool cuts, obviously not for the better. Direct cooling significantly reduces this tendency. It keeps the cutting zone clean, keeps the action consistent.
Got it. And there was one more point about dimensional stability, especially for long parts.
Right. When you're machining, heat doesn't just go into the tool, it goes into the workpiece too. For long, slender parts, that heat can cause thermal expansion or even distortion, bending. Makes it really hard to hold tight tolerances over the whole length.
So the direct cooling helps the part stay true as well.
By lowering the overall temperature right there in the cutting zone, yeah. It helps maintain the dimensional stability of those sensitive parts, less thermal distortion.
It's really quite amazing, isn't it? That cooling, which sounds simple, becomes this precise science, like the material says, hidden away in these tiny channels.
That targeted delivery, that's the secret sauce, delivering the fluid exactly where it needs to be.
And the benefits just stack up, according to the source.
They do. Longer insert life, less machine downtime because you're not stopping to change tools constantly, quicker setups because the process is more predictable, an overall optimized operation.
Okay, so that's tackling the heat side with precision cooling. Let's pivot now to the other half, controlling those chips. The material says the chip breaker is fundamental, but often overlooked. Why overlooked?
Well, maybe it's just less, visually dramatic than seeing high-pressure coolant spray. But poor chip control is a constant headache.
Especially during finishing or when the cut depth changes.
Yeah, exactly. Those long, stringy chips are those horrible birds' nests. They're dangerous, they're hard to handle, they can wreck the part surface.
And the material highlights Iscar's work here, developing new geometries.
Yes, developing new chip breaker geometries designed specifically to handle a really wide range of materials. Things like steels, stainless steels, even tricky superalloys.
Okay, so break it down for us.
Yeah.
How does this little feature, this groove, actually make the chip behave?
Well, the core idea explained in the source is this precisely engineered arched groove right near the cutting edge. As the metal peels off the workpiece, forming the chip, it hits this groove. The shape forces the chip to curl up really tightly.
Right.
And because of that geometry and the material properties, it causes the chip to break. It snaps off into short, manageable bits instead of becoming a long, dangerous ribbon.
So it forces the chip to kind of self-destruct into safe little pieces. Smart. And that breaking action must have a whole cascade of benefits.
It really does. Good chip breaking prevents those awful tangles around the tool or the part. It dramatically cuts down vibrations during the cut.
Which is huge for surface finish.
Critical. It extends tool life, minimizes the risk of the tool just suddenly breaking because the forces are more consistent. It even helps lower cutting resistance and generates less heat.
Working together with the cooling we just talked about.
Absolutely. They work in concert. It all adds up to more predictable, reliable machining and, yes, definitely longer insert life.
So choosing the right chip breaker geometry sounds just as vital as the cooling channels. And it's clearly not a one-size-fits-all situation.
Definitely not. The material really stresses that picking the right chip breaker depends on, well, several things.
Like what?
The specific material you're cutting, for sure. Then the cutting conditions, your speed, your feed rate, the depth of cut, and also what you need from the surface quality. Finishing is different from roughing.
You have to match the chip breaker to the job.
To get the best results, yes, you absolutely do.
Okay, so we've got this precision-engineered direct cooling, handling the heat, and these advanced chip breaker geometries managing the physical chips. The material seems to make a really strong case for the power of bringing these two together.
Yes, that's presented as where the real magic happens. The source argues it's not just about having good cooling or good chip control in isolation.
It's the combination.
The proper combination, as they put it. The right chip breaker design matched with that targeted direct cooling system that's highlighted as the key. The key to unlocking peak machining performance.
Achieving that accuracy, consistency, efficiency.
All of it. They're presented as complementary innovations. They reinforce each other, tackling those fundamental problems from two angles at once.
And the result, according to the source, is an improvement across the board.
Exactly. The material shows the synergy boosts pretty much every critical metric. Tool life gets longer, surface quality is drastically better, and the whole process becomes more stable, even in really tough, high-volume production.
So, stepping back a bit, the core message, the big takeaway from this source material, seems to be that managing heat and controlling chips, it's not optional anymore.
Not just minor tweaks.
Right. Things like sophisticated coolant channel designs, smart chip breaker geometry, they're described as the absolute foundation of modern high-performance metal cutting.
And understanding this, it matters to you, the listener, because these seemingly tiny hidden details, how a tool deals with heat, how it manages chip flow, they are fundamental.
Fundamental to making the precise parts that underpin so much of our technology.
Everything from car engines to critical aircraft systems, yeah. It all relies on getting this right.
It really does make you appreciate the sheer amount of engineering packed into something as small as a cutting tool insert. Think about that unseen science inside it, like the material describes. That precise path the coolant follows. That subtle, exact curve of the chip breaker groove.
It's not just clever design. The source suggests this is where intelligent solutions really drive value, drive those technological leaps in manufacturing.
Yeah. And consider the scale of impact these innovations have when you're talking about mass production. Achieving that accuracy, that consistency, part after part, thousands or millions of times.
It's a powerful reminder, isn't it?